Welcome everybody to the Namboodiri lectures. For those who are new, Namboodiri was a student of mine who died in a car crash a week after defending his thesis. His parents donated money to the department to set up a lecture series in his honor. I don't remember the year in which it started, but it would probably be in the 1980s. And it's been going on ever since. It's expanded from algebraic topology to geometric topology. And today we have Ozsvath, who will tell us about Heegaard diagrams and homomorphic mathematics.
Thank you. Thank you. It's an honor to speak in this series, and thank you all for coming to my lectures. I know it's presumptuous. A few weeks ago, Peter asked me to send titles and abstracts, and I dutifully did that. And an hour ago, I was thinking about how I'm going to say things, and I realized that I would prefer to take the lectures in a different order. Unless there are objections at this moment, I'm going to probably give the second lecture first. So the choice is whether we start high in the sky or concretely with things you can draw pictures about. And I think I'll opt for the second of those, to talk about something concrete and specific, and then if you want science fiction, you'll come back for the next lecture. Okay. So I'm going to describe here invariants for low-dimensional manifolds that arise from, that were motivated by ideas from symplectic geometry, Floer homology. And when I'm talking about low-dimensional topology, I'm being intentionally somewhat vague. So for me, four-dimensional topology means either knot theory or three-manifold topology or smooth four-manifold topology. So what I'm going to focus on today is knot theory, and I'm going to start by focusing on just more general questions about knot theory, and then I'll gradually move my way towards Floer homology. Okay, so what's a knot? So for us, a knot is a closed loop in 3 space, an R3. It's an embedded copy S1 in R3. And, if you move through embeddings, then you get what are called isotopic knots, and we think of them as the same. So here's the second simplest knot, called the trefoil. Here's the simplest knot, called the unknot. But knots could get more complicated, and so here's another knot. That's called the 2-5 torus knot, because it's got 2 strands. They go around 5 times, sitting on a torus. So that's another example of a knot. So the first question you might ask is, how does one measure the complexity of a knot? So if I look at a knot, how can I tell how knotted it is? So here's a definition of a knot, of complexity of a knot, that one can explain to a non-mathematical, a very friendly non-mathematician, an ally, but a non-mathematician, or a kid. Anyways, the definition is the following. So suppose I have a knot, and when I'm not allowed to, my knot is made out of metal. It's not allowed to cross itself. But at some magic moments, I'm going to allow myself to snip it and then reconnect it after I pass it through it. So I'm going to allow some change, where I change the knot, I bring 2 strands together and pass one through the other. And one can ask, given a knot, K, so here I might bring those 2 strands and cross them. You see, those 2 strands, I cross them through each other. What's this knot?
The unknot.
It's the unknot. So So one can ask, given an arbitrary knot k, what's the minimum number of moves of this type required to pass to the unknot? And that's called the unknotting number of a knot. It's a very simple definition. It's not as simple as you might think. So I don't mean you take a picture and do the crossing changes locally, but I'm imagining the knot is living in 3 space. So I'm minimizing over a rather big space of all, I can bring 2 strands together in kind of infinitely many ways. So what is this minimum number? So this is a number which is as easy as it is to define is how hard it is to compute. So it's known for small knots. The unknotting number of, well, the unknot has unknotting number 0. I don't have to do anything to it. The trefoil we've just demonstrated has unknotting number 1. Well, I guess I didn't demonstrate that the trefoil isn't the unknot, but it isn't. Take my word for it. So it has unknotting number 1. This creature over here, you see that there's a crossing here. If I change it, then just as the trefoil turned into the unknot, this guy turns into the trefoil. So what we have is a sequence of 2 steps that takes this knot down to the unknot. So, but that doesn't prove that it has unknotting number 2, because maybe some really clever person finds a different embedding and a different pair of strands to cross. But it turns out that this knot does have unknotting number 2. One can prove that. There are other numerical invariants that give you lower bounds on the unknotting number that, in this case, are shown. 8 minutes into my talk, let me give an open problem. So, I guess I have to give a definition. So, if you have 2 knots, you can form what's called their connected sum, which is, informally, I tie one knot, and then I tie the other knot, and I bring them together. But it's a connected sum operation, where I just meld them together like that. So it's not hard to see. This is called the connected sum of 2 knots. It's not hard to see. If I've got an unknotting sequence for K1 and an unknotting sequence for K2, that's of course an unknotting sequence for their connected sum. And what that tells you is the unknotting number of K1 plus K2 is less than the unknotting number of K1 plus the unknotting number of K2. That's easy. It's conjecture. This is not known. So what does it mean? What it means is that maybe one could use this space as some extremely clever way to find a smaller unknotting sequence. This is verified for all knots with reasonable numbers of crossings, but it's, as it stands, an open question. Okay, so this is all I wanted to say for a while about the unknotting number. It's easy to define an invariant. Don't have to set up a lot of theory to define it. And we know very little about it. There's no algorithm for computing the unknotting number. There are many open questions about it. Okay, so let's talk about easier to understand invariants. Are there any questions? Yes?
Does it become simpler if K1 is equal to K2 or if it's a multiple of a single knot?
No. No, I mean, this is, I guess, still an open question, whether n times k has a unknotting number, n times that unknotting number.
Is there a lower bound on how complex it is to compute the unknotting number?
There are many numerical lower bounds on the unknotting. If you give a diagram
on the complexity of the problem.
I don't, none that I know of. Okay, so. Let me give now a more complicated to define, but much easier to understand invariance. How it goes in life, right? So there's something called the, what should I do next? Yeah, I'll do the cyclogens. So it is also true that any knot in 3 space can be realized as the boundary of a surface. So for instance, the trefoil over here is the boundary of this triply twisted no-use strip, right? But I don't like that because it's not orientable, so I can't do Green's theorem on it. So instead of Stokes' theorem. So instead, I can also realize it as the boundary of an orientable surface, and the orientable surface in this case is this triangle. It's maybe easier to draw from this perspective. This is another picture of the trefoil. I take this piece of this creature and this disc, and I attach them to each other along 3 twisted strips. And that's now an orientable surface. You can see it's got an upside and a downside. And its boundary is the trefoil. All I've done is you could draw the picture over here too. Then the second thing looks down here. Okay, so and now we can. This is called a ciphered surface. So if K is a not embedded in R3, then there exists an orientable surface F such that the boundary of F. And there's a classification theorem of surfaces which says that a surface with one boundary component has an orientable surface with boundary component has a single, its homeomorphism type has a single invariant, which is the genus. So it's gotten by taking the disk and adding a bunch of, I think of these as telephones, but I think that just exhibits my age. So, but you add these handles to this disk, and that's the number of those is the genus of the surface. And here's a cute exercise. This surface that I've drawn is homeomorphic to genus 1. It has genus 1 surface with one boundary component removed. Notice that the homeomorphism is intrinsic. It doesn't extend to R3. But now we can ask, given K, so of course, there exists an orientable surface. There are many different orientable surfaces, and they have different genera. I could take this guy and add, just for fun, extra handles and up the genus. But one can ask the following question. Given K, what is the minimal genus? For any ciphered surface. And that's called the ciphered genus. So, turns out that so of course it's pretty clear that G of K equals 0. Maybe I should just say this. The unknotting number of K is 0, obviously, if and only if K is the unknown. It's also true that the ciphered genus of K is 0, if and only if K is the unknown. It just means that the K bounds a disk, so you can make it unknown. The trefoil, therefore, has a ciphered genus 1, and it has ciphered, and the 5-2 knot has 2-5 torus knot has ciphered genus 2. Great. Here's a theorem. The ciphered genus, when connecting some of 2 knots, is some of the general of the cipher. This is not a difficult theorem. One uses, it's in chapter 1 of Lickerich's book on knot theory. It uses combinatorial. So the cipher genus does behave nicely. It's not particularly easy to compute. So it's an example of a thing that is a little harder to define than the unknotting number. It can be computed, but it's not not always an easy numerical invariant to compute. So let me move on to another one that actually is, unless there are any questions. Any questions?
Can you give a minimal example of a knot whose First invariant is different from that.
Oh yeah. So I guess the yes, I can. Let me hold off on it because I want to save it as an example for something else as well. Okay. So I'm now going to define a third invariant, which is quite easy to compute. It's maybe the definition I'm going to give is an extremely elegant formulation due to Conway. This is the Alexander polynomial. I'm going to give Conway's formulation, which is extremely elegant and very sort of like. Sometimes in mathematics, when something is so elegant, you have no idea where it came from. So those are kind of definitions you want to give in a colloquium style talk. We'll do that. So the Alexander polynomial is a function from knots in S3 to long polynomials in T. The formal variable T. And it's characterized by the following two properties. Is the unique function from knots such that, first of all, the Alexander polynomial of the unknot is the constant polynomial 1. And the second is what's called the Skene relation. Skene relation says that the Alexander polynomial of this knot, I draw a picture of a knot and I find some crossing in it. I orient my knot and it has some crossing in it that looks like that. And I subtract off the Alexander polynomial of this knot. Then I get t to the 1/2 minus t to the minus 1/2 times the Alexander polynomial and now a white lie of the knot that I get by what's called resolving that crossing. That means I erase the crossing and turn it like that. Now, the white lie is that this is not actually anymore a knot. What happens is, for me, if you think of a knot as being a single closed loop, and you play this game, then all of a sudden the number of components is going to change. So we have to generalize from knots to links. Links are multi-component knots. We want them to be oriented. We want each component to be oriented, and sadly, the coefficients are really t to the 1/2, t to the minus 1/2, because of this 1/2 minus 1/2. But for knots, it turns out that you don't need the halves. Okay, so this is now the Alexander polynomial. And it's remarkable that this is well defined. I've just given you this formula, and what's remarkable is that you can actually, this works and gives you a knot in it. Are there any questions so far? Okay, yes?
If you have a union of unknots, is there some normalization on the union of unknots as well, or is that?
It turns out that a union of unknots has Alexander polynomial 0. So we don't need to normalize. This is the normalization that's sometimes not the one used. Sometimes, for some purposes, it's natural to take 1/1 minus t instead. Okay. All right. So this, you can use the Skene relation and just compute the Alexander polynomial of the trefoil. You do that. Find that, well, this we know, this has Alexander polynomial equal to t minus 1 minus t inverse. Okay, this has t squared minus t plus 1 minus t inverse. It is now no longer true that the Alexander polynomial being 0, if and only if the knot is an unknown. And the Alexander polynomial not being 0, in this case, would be 1. So there are non-trivial knots with Alexander polynomial 1, and in fact, there are many, many of them. And there are 2 that I can draw in a public talk. 3, maybe? Include the unknown. This is the celebrated Kiyoshitatera knot. I've drawn a 12 crossing projection, and it is a knot which has the property as Alexander polynomial is identical. So it's not. So that tells you the shortcoming of the Alexander polynomial. Incidentally, it also has unknotting number 1, and its cipher genus is 2. So that's also an example for your earlier question. Okay, so let me just, while I'm listing properties, the Alexander polynomial, if you like the sum of 2 knots, is the product of the 2 Alexander polynomials. So it behaves nicely in the and there's actually an interesting relationship with the cipher genus, which is that the degree of the Alexander polynomial is a lower bound than the cipher genus. Where by degree, I'm being a little bit funny. This is a knot which is a symmetric Laurent polynomial. So by the degree, I just mean the maximal d power that's not 0. The minimal d power that's not 0 is minus d. So this d, which should be more explicit. The Alexander polynomial can be written as sum of a sub I t to I goes from minus d to d, such that a sub d is non-zero. This d is what I need. So that gives you a lower bound on the cipher genus. But it's not a sharp lower bound because the degree of this was 0, but the cipher genus of this knot is not. So the Alexander polynomial is a lovely invariant. It's been around for, it's celebrating its 100th birthday. And it can, nice to compute, but it has some shortcomings. Okay, so these are not invariants that I wanted to describe, but maybe I should describe a last not invariant, which is in the spirit of the unknotting number. It's an invariant that we don't understand so well. And that is, that's what's called the slice genus of the knot, or the four-ball genus of the knot. So if we take the four-ball, which I'm going to draw deceptively like this, then, in fact, I could draw even more deceptively like this, four-dimensional disk. I can think of my knot as somewhere living on the boundary of the disk. And I can ask myself, what's the minimal genus of an embedded surface in the four-ball that meets the knot along the boundary? So let me now try to convince you that this is a natural thing to think about. Let's think about the unknotting number of a knot. If you unknot a knot, then what do you get? You have a movie where your knot's moving around in three-dimensional space. And there are these kind of miraculous moments where the knot passes through itself, and it ends up being the unknot, and I can attach a disk to it. What is this movie? This movie is describing for us a disk in force space, which is R3 times positive time, where at t equals 0 we have the knot, and as time progresses, this disk sometimes intersects itself, which is when the two strands try to pass through each other, and then the knot gradually disappears. So what I've done is I've constructed what a topologist would call an immersed disk in the four-ball, whose boundary is the knot K. And there are those moments, those tragic moments where the knot crosses itself, those are like, if you like, if you think of those as complex coordinates W and Z, it's the two coordinate lines, W times Z equals 0. Right? That's the unit of those two complex lines that meet at a point. Okay? And now, well, that's not an embedded disk. That's not an embedded surface. No, we can turn it into an embedded surface by W times Z equals epsilon. W times Z is epsilon is an annulus. It's not a, right? So W times Z is annulus. Gives an entertaining exercise. You can see that topologically the solution space is an annulus. So what we've done is we've replaced this double intersection by a little annulus. So what we've effectively done is that we've formed self-connected sums of this disk with itself as many times as we have steps in our unknotting sequence. So now we've exhibited a particular surface in four-dimensional space whose genus is equal to the unknotting number, say, of my knot. And now we can ask, can I do better? What's the minimal genus of any embedded surface in this four-dimensional ball that meets your knot along the boundary along? And this is called the slice genus. So it'll look almost exactly. What's the minimum genus of any surface F embedded in that? And now, this is a the movie that I played for you earlier exhibits the following inequality. The four-ball genus of K is less than or equal to the unknotting number. An unknotting sequence K lies to the embedded surface. That's tautological. Also, the four-ball genus of K is less than or equal to the cipher genus of K. That's pretty clear. If you have a cipher surface for the knot, you just push it into the four-ball, and that gives you this inequality. But this, again, is also a kind of invariant that's opening the doors from kind of the low-dimensional topology world that we all are comfortable with, because it's three-dimensional space, and we were born in three-dimensional space. And this is where we enter the world of smooth four-manifold topology, because you're going to ask, what do I mean by an embedded surface? I could mean it in the suitable topological category, or I could mean a smoothly embedded surface. And questions about this slice genus actually this has been around for a long time, but interesting results about the slice genus only kind of came around. So questions about the smooth slice genus of knots were answered only after the invention of gauge theory, which were modern techniques to study smooth four-manifold topology. Okay, so I have now, yes?
Can you just repeat what the definition of the slice genus is?
Okay, the slice genus or four-ball genus of a knot is you realize you can draw your knot K as living in S3, which is, of course, the one-point compactification of R3. And then the question is, what's the minimum genus of an embedded surface in the four-ball whose boundary meets the boundary along exactly the knot?
Okay.
Okay? Great. So this is a kind of question that one wants to understand. And maybe I'll just say here that you might play with what's called the PQ torus knot. What's the PQ torus knot? I sort of told you. I take P strands and I twist them Q times. They probably did exactly the opposite of the way you're supposed to. No, I do them Q times and I bring them all the way around. So that's the PQ torus knot. So like for instance here, this is going to be the 3-4 torus knot. Formally, you take the standard torus living in R3, you take P points, you twist them around, and then you get the PQ torus knot. Now, in the 70s, I guess, Milner conjectured that the unknotting member of the PQ torus knot is equal to the 4-ball genus of the PQ torus knot is equal to the 3-slice genus, the cipher genus of the PQ torus knot, which is easy enough to compute to be P minus 1 times Q minus 1 over 2. So this was conjectured by Milner and proven by Kronheim and Rivka. In the early 90s. And their proof used gauge theory and four manifold invariants. So what I would like to talk about now is and since their proof, there have been other proofs. There's it also follows, their proofs use Donaldson theory. That proof just imports the Cyber-Witten theory. There was also a very beautiful proof by Jacob Rasmussen using a different non-invariant, which Heegaard homology, which I'm not going to say too much about. But what I would like to talk about is another non-invariant that can be used to prove this theorem and can be used to say things about these other quantities as well. So that's going to be what I'll do next, sort of. Are there any questions? Okay, so I'm going to give you now a definition which is very much in the spirit of Conway's definition, in the sense that it does obscure the sort of mathematical history behind the construction. So I want to give you an invariant, but actually before I give the definition, I want to describe some properties. So the invariant I'm going to describe now is an invariant called non-Floer homology. It was defined by me and Zoltan Szabo and independently by Jacob Rasmussen. It's an elaboration of Heegaard Floer homology, which I guess I'll describe in the second lecture. And this was defined around 2003. And it now has some purely combinatorial formulations. At the time we defined it, it was defined using holomorphic disks and so on. But I'm going to describe a formulation from 2006 discovered by Ciprian Manolescu, myself, and Sucharit, and further elaborated on by so the Manolescu. So this is a combinatorial computation of it, and this is a combinatorial proof of the invariance properties as well. So, and finally, I guess I should say, there's a book called Grid Homology for knots and links, which was written by the Rasmussen, Zoltan Szabo, and as a salesperson, I will make a pitch for this book. It's a book, and you can get a certified kosher free copy from my homepage. We negotiated with the AMS that after 2 years it could be freely downloaded. So download it and then fall in love with it and buy it if you want. It's okay. All right. So this is the invariant I'd like to describe next. But before I do it, I want to say what its structure is. So grid homology is or not for homology, is an invariant for knots in S3, or knots in 3 space, which has the following structure. It's a bigraded abelian group. It's a bigraded vector space. I'll put a hat over here. Bigraded vector space. Let me just say over Z2, because I'm lazy about signs. There's actually a refinement of this to integer coefficients. But it's a bigraded vector space. What does that mean? That means that it's a vector space which is equipped with a splitting into 2 summands, 2 integer-valued summands, which I write like this. D as a subscript and S is just next to it. For those of you who are familiar with homology theory, that's a vector space, a graded vector space associated to topological space. Homology classes have a dimension, which is a number d bigger than or equal to 0. Well, here our d's can be negative, and we have another number, which is called the Alexander grading. So this is called the Maslov grading, and this is called the Alexander grading. So this is a finite dimensional vector space. Look, if you're going to think about it very concretely, you have this kind of SD plane, and over each lattice point in the SD plane, we have a finite dimensional vector space. But in all, everybody's finite dimensional. So that means that after a while, you run out of gas, and everybody becomes 0-dimensional. So we've got these finitely many lattice points, each of which are labeled with non-negative integers. That's what the structure that not for homology is. And let me now give some not for homology groups. For the unknown, all of not for homology is concentrated over the origin. You have a 1-dimensional vector space right at the origin. For the trefoil, we have a 3-dimensional vector space living along this diagonal line pushed off from the origin. There's a copy of F here, a copy of F there. For the 2-5 torus knot, again, it lives on a diagonal, and it's 5 copies of F. Okay. All right, wonderful. We've got a bigraded vector space. What do you do with a bigraded vector space? Well, what do you do with a graded vector space? The first thing that you want to do is you want to take its Euler characteristic. So Euler characteristic of a space is you take its singular homology, and you take the alternating sums of the dimensions of the homology groups. So we'd like to do that here too, except what do you mean by alternating sums? There are homology groups sprayed all over the plane. Well, what I'm going to do is I'm going to take the alternating sum in each of these vertical slices, and I'm going to have that be the coefficient of the power of t to the s. So graded Euler characteristic in the sense of Hovanov of this bigraded vector space is equal to the sum of -1 to the d t to the s times the dimension of hfk hat dk x. So we get the Euler characteristic of this creature in a natural sense is the Laurent polynomial. So if first there was Euler, and he computed the Euler characteristic. And then we had singular homology, which is a refinement of the Euler characteristic. It's a graded abelian group whose Euler characteristic is the Euler characteristic. Well, in the same way, if you take the Alexander polynomial, we now have a bigraded homology theory whose Euler characteristic is the Alexander polynomial. Oh, I didn't say that. It turns out that this graded Euler characteristic is equal to the Alexander polynomial. So that's clear here. We get t to the 0 times and s 0. We got 1. Here, this guy contributes t. This is in dimension -1, so this is -1. And this contributes a t inverse. So we get that there, and so on. Okay, so this is a refinement of the Alexander polynomial. Well, let's think about this creature right here. It turns out that the non-flow homology of this Kinoshita Terasaka is this. I'm just going to write dimension. Oops. Put some chalk in there. So I'm just going to write the dimensions. 7, 4, 1, 1, 4, 6, 4, 1. So we see a large dimensional vector space. And we see that when we're taking the Euler characteristic in this direction, we have 1 and 1, which are in consecutive dimensions, so they cancel. 4 and 4 in consecutive dimensions cancel. The 7 and the 6 turns into a 1. So the Euler characteristic of this is 1, and yet the not-flow homology is quite rich. Okay, so we see that the not-flow homology is in some sense better than the Alexander polynomial. And what I want to say is that there's even more. I apologize for whoever is trying to watch this on a video. They'll see the theorem I wanted. The theorem that I wanted was that remember there was a theorem that said that the degree of the Alexander polynomial in a suitable sense is the lower bound on the Seifert genes. But then this inequality is not sharp. But the corresponding inequality for non-flow homology is sharp. Theorem in the Zoltan Szabo, which says that if you think about this blob of points on the plane, then the distance out from the s equals 0 axis is equal to the Seifert genus. So that is to say, the Seifert genus of the knot is equal to the maximum s such that the not-flow homology in Alexander grading S is non-zero. So not-flow homology detects the unknot. Oh, sorry, correlate. Not-flow homology detects the unknot. That is to say, the not-flow homology, the dimension of the not-flow homology is 1 if and only if k is 1. Okay, so this is the kind of sort of topological information that not-flow homology does have in it. See, the other thing that I can say is that this is a theorem from around 2003. There's an alternative, very beautiful proof due to Juhas in 2004, where he develops a theory. This proof kind of used every piece of topology that I knew at the time and more. But so it starts from Gabai's suture, manifold theory and goes from there to symplectic geometry. And from symplectic geometry, it goes to the Handel decompositions of symplectic manifolds of Donaldson, and from there it goes to the four-manifold invariant constructed in a Heegaard Floer homology, and from there it ends up ultimately in not Floer homology. So it's a long kind of stroll through mathematics. And Juhas gave a very elegant construction that goes straight from Gabai's sutured manifold hierarchy to a version of Floer homology for sutured manifolds. So he was able to give a much more sort of contained proof of this there. And more, but maybe I won't go into the more right now. But I wanted to say one other thing, which is that there is an invariant. Now I see that it's a little sad that it's called, oh no, it's not called anything sad. There's an invariant called tau, which is an invariant of knots, and it's an integer. And it can be extracted from this chain complex in a way that I don't want to go into right now. But it has a lovely property that it is additive under connected sums. And more importantly, it gives a lower bound on this formology of K. So it's an invariant. It's not the only invariant of this kind. The first invariant is what's called the Murasugi signature. It's a classical invariant which has these properties. But tau has the wonderful property that tau of the PQ torus knot is equal to P minus 1 times Q minus 1 over 2. So tau, together with this property, then actually gives you an immediate proof of the Milnor conjecture. So that's another piece of algebraic information that not homology has. Maybe along the lines of what we knew and what we had. Remember I said that the Alexander polynomial of the connected sum of two knots is the product of the two Alexander sum polynomials? Well, there's a corresponding statement that not Floer homology of the connected sum of two knots is the tensor product, the not Floer homology of K1 with the not Floer homology of K2. And by tensor product here, I mean the bigraded tensor product. It's the thing that plays a natural analog, multiplication of polynomials. Okay, so I think I've now said the structure and what motivation I want to give for not Floer homology, and what time is it? In my remaining 11, when do I end?
5 o'clock.
5 o'clock. My remaining 11 minutes, I'll attempt to give a definition, unless there are any questions. Yes?
So the scaling relation?
Yes, yes.
Does that have an analog in?
Yes, it does. The skein relation, that's an excellent point. The analog of the skein relation is an exact triangle. So the three terms in this skein relation sort of turn into three terms in an exact triangle that relates the knot Floer homology of those two knots and a link. And yeah. Any other questions?
Did you explain what the relationship between tau and your...
No, I didn't. I left that. I swept that under the rug. But I will come back to it. Any other questions? Okay, so I want to now attempt to give a construction of not Floer homology. I'm almost certainly going to run out of time, but then we'll just continue where I left off next time. So I'm going to now give not, of course, the original definition, but I'm going to give the construction of Manolescu and mine and Sarkar. So the starting point is, how do we describe a knot? So the way I've been describing knots, I've been saying it, and I've been drawing planar projections. I try to draw the knot on a plane, and you get a curve with double points on the plane, and at each double point you decide which is the upper and which is lower. But there's another very convenient way of describing knots, which are called grid diagrams. A grid diagram is an n by n grid of squares on the plane, decorated with O's and X's, distributed according to the following rule. Each column has exactly one O in it. Each row has exactly one O in it. Each column has exactly one X in it. And each row has exactly one X in it. And the claim is that a grid diagram like this specifies a knot projection, and the rule is the following. I'm going to just connect the vertical O with the vertical X. And horizontally I do the same thing, only the understanding now is that the horizontal passes under the vertical. And if you stare at that picture, if I had drawn it with my beautiful colors that were provided to me, you would see staring at you the trefoil knot. So this is a way to represent knots, which is lovely, and it was discovered in 1898. So it's a long. It's been around for a long time. It's been rediscovered many times since. So now for us, we're going to represent a knot as this grid diagram, which I will now redraw because I made it messy. Oh. Now, for symmetry, I can think about this grid diagram as living not on the plane, but rather on the torus. So there's a symmetry, which is I could just take this top row and stick it on the bottom. That wouldn't change the knot type because I'm moving the I move horizontals back. I can always move the horizontals back, and the verticals I can move back down. So this picture is symmetric. I can think of it as living on the torus. And now I want to define to this picture a chain complex. And that chain complex is going to have generators. That grid diagram has an n by n grid. Then I'm going to have n factorial generators. So if you like, we've specified the knot by a pair of, these are elements of the symmetric group on n letters, right? These are two permutations on n letters that have some property. The one times the other should be a cycle if you want a single knot. If it's a product of different cycles, then that's something. Okay, but now I want I want to define a chain complex. The generators are what we call grid states. So these horizontal lines now we think of as circles. A grid state is a n tuple of points, where one point lives on each. There are n tuples of intersections between the horizontal circles and the vertical circles, and they're distributed so that each horizontal circle has exactly one point on it, and each vertical circle has exactly one point on it. So in other words, it's the graph of a permutation on n letters. So these are going to be our generators, and I'm going to add a little bit of algebraic structure. I'm going to label my O markings. And I'm going to define a chain complex over a polynomial algebra in n variables. So the generators of this, I'm going to call it grid complex of my grid diagram is going to be, my generators are these elements of permutation group on n letters. That's a copy of this free module over this polynomial algebra. And now I have to define what the differentials are. So the differentials count rectangles. What kinds of rectangles are there? What's a rectangle? If I give you two grid states, here's a grid state, here's another grid state which agrees with it here, it's different from it over here, different over here, agrees here, and agrees here. I got a blue grid state and a red grid state, and they differ in exactly 4 spots. Then I can divide my torus into 4 rectangles, which have as their corners the 4 dots where the 2 grid states are not the same. Okay? So I'm going to redraw this sort of more abstractly. if I've got a grid state P, and I've got another grid state Q, and everywhere else, the P and the Q are the same. Group theoretically, that's saying P was specified by an element of the symmetric group, Q is specified by another element of the symmetric group. If those two elements differ by a multiplication by a transposition, then they differ in only these two spots. Then I can divide the torus into these four rectangles: A, B, C, and D. And I want to just make the following convention. I want to think of A as a rectangle that goes from P to Q. And I want to think of D as also another rectangle that goes from P to Q. And I want to think of B and C as rectangles that go back. So what do I mean? The rectangle is an oriented quadrilateral. And what I do is I look at its boundary. Horizontally, I'm going from P to Q. Here. Horizontally, I'm going from P to Q. And over here, horizontally, I'm going from Q to P. So these are that's the explanation for those directions. So, so given P and Q, I can look at the space of rectangles from P to Q. That's always either empty or it has two elements. It's empty if the things don't differ by just a transposition. Otherwise, it has exactly two elements in it. And now, for Blackboard choices, I can write a definition of a differential. The differential of P is equal to the sum over all states Q of the sum over all rectangles from P to Q times some coefficient times Q. But I don't want to look at all rectangles. I want to exclude rectangles in the following cases. Here's a rectangle. If it contains a PQ point in its interior, then I don't want it to count. So I want only those rectangles such that R interior of R intersect P. So did I erase it? No, I didn't. Okay, but that's not relevant. Here's a rectangle from blue to red. This is a rectangle from blue to red, but it's excluded because it has a blue-red point in its interior. Okay, I want that, and I also want the X markings. I want it to be X-free. So this rectangle is also excluded by my now demands. And now I have to tell you what the coefficient of Q is. It's going to count the number of times O1 appears in my rectangle, and use that as U1. Number of times U2, and that's U2, that's U2, to UN, so ON. So it just...
Sorry, is that number either 0 or 1?
Yes, that number is either 0.
Okay.
We got a rectangle, let's say it contains O3 and O7, then it contributes U3 times. Okay, that's the chain complex. Why is that chain complex? D squared equals 0. How do you prove that D squared equals 0? It's a combinatorial argument that has to do with how rectangles in the torus can interact.
And you don't even put any sign here.
Oh, that's just because I was lazy and I was working over ZMOD 2.
Ah, okay.
If you work on a double cover of the symmetric group on n letters, then there's something called the spin double cover. Then you can put in signs.
Okay.
So D squared equals 0, and this is this is like some kind of very sad combinatorial leftover of Gromov's compactness theorem. So, but D squared equals 0, so you can take the homology with respect to this differential, and you end up with a chain complex over a polynomial algebra in n variables. And it turns out that any of two of those actions is homotopic to each other. So you can think of it as a chain complex over a polynomial algebra in a single variable. Or you can set that variable equal to 0 and take its homology, and then you get the Knopfler homology I was talking about over there. I didn't talk about bigradings and The other thing I didn't talk about is invariant. So you can prove it independently. So this turns out to be a non-invariant. This would be surprising. It depends on a grid diagram. But one can prove it invariant independently. Okay, so maybe I've run out of time, so I'll stop here.
Other questions?
Yes.
You chose a torus.
What's that?
You chose a torus.
Yes.
Why?
Why? I could have worked in the plane. But if I worked in the plane, I want to count this as something in the differential. So from the point of view of the torus, this just looks like a rectangle, whereas from your perspective, it looks like two rectangles. So, right, it looks like this union this.
Why not say the sphere, the other identification?
Well, hang on, so the sphere is not the other identification, but you can draw, there's an analogous picture you can draw of the sphere. But the torus has the maximal amount of symmetry. If you formulate you see, if you tried to work on a sphere, then you would have to have, yeah, so, right, so I guess my point is that you want to take the square, so you're going to have to, in this picture, you've got to do something to the square. And the natural symmetry of the knot diagram says that this is like working on the torus. But there are analogs in this story that work on other Riemann surfaces. There's a theory that works on the sphere, but it's a little more complicated to describe the differential. There are also versions that work on the surface of genus G, but there you have to choose the homomorphic structure. So upping the genus is a bad direction, but lowering it is a good thing. Good one. This is just more. Yes?
What's the title of the paper you referenced? Johas 2004?
What's the title? I guess Sucharit Floer homology. There's several papers. I can give you a more precise reference if you like by email. Just send me an email. Or look on the archive under UHAS for all the papers that he put on the archive between 2003 and 2005. There's more than one paper where he proves these properties.
If you were to sort of take a Thurstonian point of view of knot invariance, you would look at knot complements, and then you would start doing hyperbolic 3 manifolds.
Yes.
So, presumably, this kind of point of view also extends to a world beyond knots. And like, do these type of things play together well, or is there kind of a weird mixing space where like they knots are together, or is it like just totally different?
I think the short answer is that it's still quite mysterious. This is, as best as I can say, a different perspective than hyperbolic geometry. And in fact, like that we we milked that difference in some ways. But the honest answer is that that's not well enough understood. But I'd be happy to talk some more.
So you explained that there's a uniqueness of the Alexander polynomials, right?
Oh man, that's a great question.
Could you repeat the question?
Is there a uniqueness statement for Floer homology? Is there you might make some kind of conjecture that there's a unique theory that has. Okay, the short answer is I don't know. And the longer answer I'd be happy to subject you to after we've let people who want to go away.
Is the extra structure needed to play this game on a GSU surface just using a complex structure, but more particularly like would a translation surface? Like, is that sort of what you?
I don't know what that is. So I guess the answer is no or yes.
Like an affine structure with singular points.
Okay. No, it's a Riemann surface structure is what I think that really means.
sort of singular Riemann surface or something.
Let's thank Peter again. So the next talk will be Monday, 4 o'clock in Ryerson 251, and there will be tea before the talk Monday.
I remember